Okay, so last we were discussing Langevin equation, and then we looked at the mean square displacement, right, from the Langevin equation. So, mean square displacement is a fundamental quantity we are all interested in. So, this is the expression we had for the mean square displacement of a particle, right, of a Brownian particle, that is at a specific time t, or this is how it varies as a function of time. Now, then I briefly said that you will be having two limiting cases, right. So, one limiting case is if you would appreciate that the t is much less than the correlation time. So, remember what correlation time was. So, this time when you are measuring, or when you are measuring the mean square displacement of the particle, it is much less than what a correlation time is, which is m by xi, right. And then you see what happens. Because that exponent is very small, then you can expand. Accordingly, you do this expansion, you put it in the previous equation we had in the previous slide, right, and from there what you get is your mean square displacement x square is equal to k times t over m times t squared, or the root mean square is given by this, the last equation. Okay. So, this is your root mean squared. So, this is your RMS, the root mean squared displacement. See, what does it say? What it says is your kT by m is essentially your speed or velocity, then it is independent of the friction and all these things, right. That means, here the particle is exhibiting free motion. Why? Because the measurement time t is much less than the correlation time. So, you are measuring it at a time which is much less than the time for it takes for the correlation to decay. In other words, you have not had many collisions occurring, because the moment collisions start occurring, it is no longer a free particle. It depends upon what the number of collisions and all these things happening, right. So, that is why it says it does not depend upon the diffusion coefficient or friction and all these things. Here for very short times the Brownian particle undergoes absolutely free motion, that is what the statement signifies. Now, obviously, if this is one limiting case, then the other limiting case is when you are looking at infinite time, that is t is much less than the rather much greater than the correlation time, right, and that is what it is, and this is what we had discussed last time. Then this factor tends to 0, and this is what you have, that your root mean square displacement, again this is your RMS, is proportional to the square root of t, okay, or x square, average of x square is equal to 2 times d times t. Now, this is also I told you last time, this is a characteristic of a particle exhibiting Brownian motion, and this is what we derived from the Langevin equation, right. Can we, and I also told you one more thing, that if you would start from a random walk, that means the Brownian particle, you would also come exactly to the same point. Only then you would recognize or appreciate the fact that this is indeed a Brownian particle. So, in other words, what we would do next is we would actually try to model the distribution of a particle or a species exhibiting random walk. Random walk means you start from this position, you go here, whichever position you go to is absolutely independent of the previous position you were in. Okay. So, there is no relation to your starting point. Okay. So, that is also like a memory function, but anyway. So, the Brownian particle exhibits a random walk, and that is what it comes to. So, this is what we had from the Langevin equation. Now, let us see whether we can take a random walk problem and can we get the same thing. So, this is typically what a random walk is. A random walk is also referred to often as a drunkard's walk, right, because a person who is drunk would not remember where he was one step back. So, independent of that step, he would go in any direction, whether positive, whether negative, does not matter. So, that means each and every movement of that person is statistically what, independent of the previous one or independent of any subsequent others. So, there is absolutely no relation, that means these things are statistically independent, that is why it is called a random walk, it is a random walk model. Okay. So, now how do we develop it? So, what we do is the first thing, and which you know from quantum mechanics, now if you would like to get this ensemble average or anything, you would always want to go for a probability distribution. For example, in quantum mechanics, what would you do? You would do integration psi star, that observable operator, then psi d tau, right? And essentially remember, psi star psi is what? Your probability, right? So, in classical mechanics, what happens is, what you will see is that the average value is always given by that average times the probability distribution, then d of x or whatever volume element you are in. Now, we will soon see that. Hence, like in quantum mechanics, you knew your wave function, you knew what your probability was, psi star psi. Here we have to figure out what the probability distribution is. That means, we are trying to figure out if a particle is exhibiting random motion, how can it describe its distribution in terms of probability. That is what we will first look at. We will first get to that, and then we will try to see whether we can get the RMS value from there and whether it corresponds to the one we had from the Langevin equation. And it better do, because both started from the same principle, a random walk. Langevin had a random force, and this would be having something different, right? Okay. So, let us consider the random walk problem. And please remember this before I start this, random walk is very, very important. If you would ever give a search on Google, write this random walk in biology, there is actually a book, or in several books there are 7 chapters which deal with random walks in biology, because random walk is so important. Because random walk is pertaining to what? Diffusion, right? And diffusion is so important in biology. That is why we have to know, we have to appreciate what random walk can give us, or what we can tell from random walk. And we will see many things will fall directly from there. For example, how would you know that a particle is exhibiting random walk? You have to know that, right? But what is the criterion? How would you know that? Just me telling you would not be sufficient, right? You would want to know, why am I saying this, or why are we considering this particle to be exhibiting a random walk, right? That is what we are going to look at. So, what we do is, we start with this, we consider a very simple one dimensional case, okay, a very simple one dimensional case. And what we say is that can move independently in either positive x or negative x directions, where x is my coordinate of interest, okay, where x is my coordinate of interest, because I am talking about just a one dimensional equation, right, or one dimensional random walk right now. Okay. Now, what I do is, I say that let me take n1 steps in positive x direction. That means, if I start from a certain of a particular point, say A, I take n1 steps in the positive direction. Okay. Then obviously, I can also take say n2 steps in negative x direction. Okay. So, now what I can write is, if n, capital N is my total number of steps, then n is equal to what? N1 plus N2, right. So, this is equation 1. So, n is equal to N1 plus N2, where n, the capital N, I mean the left hand side of the equation, is the total number of steps. So, n refers to the total number of steps. Now, remember, we were going for a probability, right. So, we have to bring in probability in some sense or the other. Okay. So, now what I say is that the displacement in the positive x direction, so positive x direction displacement is given by the probability p. That means, the probability of this particle moving in the positive x direction is given by p, small p. Okay. Similarly, I can say the probability of the same movement in the negative x direction is given by q, where q is essentially what? 1 minus p, right. You guys all know from probability, simple. Okay. Now, remember all these motions are statistically independent, right, absolutely no dependence on where I was before or what direction I went before. Now, suppose I am trying to find the number of steps, the net number of steps I have taken, say in the positive x direction. Now, before that what I would do is let each step be of unit length, okay, be of unit length. It is just a simplification. If you want, you can even take it L, no problem, but I am just taking, say, L is equal to 1, does not matter what the units are. So, it is of unit length. So, I can write the net number of steps taken in the positive x direction can be written as m is equal to, what should I write now? Can I write n1 minus n2, right? So, what does it mean? See, m is the number of steps, the net number of steps I have taken in the positive direction, because I have moved both in the positive and the negative x, right. So, then if n1 is greater than n2, that quantity would be positive m. If n1 is less than n2, what would it mean? That instead of moving in the positive x, I have moved in the negative x. That is essentially what it means, right. Good. Now, think about this. I have said, or we have just said, that the particle moves a displacement of unit length, right, unit length displacement for any step or any particular step. Then if I am going to calculate the net distance moved in the x direction, which is actually x, because remember when I am doing the probability I have to put in x as a variable, then what would x be equal to? X would be equal to m times L, but L is equal to 1. So, x essentially would be equal to what? M, right. But remember, do not forget the fact that I am taking L to be 1, because x cannot be equal to m, dimensionally this is not possible, right, because x is distance, m is just what? The number of steps. So, it has to be x has to be m times L, where L is equal to 1. Okay, keep that in mind, because we will make this connection later, right. Okay. So, based on this, now what I can write is, see, from 1 equation 1 I have n is equal to n1 plus n2, that is a capital N. Then I can write m would be equal to n1 minus, what is n2 equal to? N minus n1, right. Therefore, m is equal to 2n1 minus n. Okay. So, then this would be equation number 3. See, now what I have done is I have removed n2, I have replaced that n2 by a constant n, and then the number of steps I am taking, say, in the positive direction n1. Okay. Now, if my steps are statistically independent of each other, if my steps are statistically independent of each other, what I can assume then assume in a sequence of steps, probability of moving in the positive x direction. I am just abbreviating it, I am just not writing the full thing. The probability of moving in the positive x direction, can someone tell me, is given by p to the power what? N1, isn't it? Because remember, these are all independent events, and whenever you have independent events in probability, what happens? They get multiplied, right. That is what it is, that is what you mean by statistical independence, right. But then, therefore, similarly I can write probability in the negative x is given by what? Q to the power n2. Okay, good. So, in terms of the probability distribution, I already have it. I already have the two main components, one is p to the power n1 and the other one is q to the power n2. There is a relation between n1 and n2, and then there is a relation between p and q, where q is equal to 1 minus p. Okay. Now, but this is not all. If I am going to look at a distribution of taking n1 steps out of a total number of steps which is n, right, where p and q are given like this, that means they are essentially statistically independent, then out of n steps I have actually two pools, right, one n1, one n2, right. Then what type of distribution am I going to get? I am going to get a binomial distribution, right. I am going to get a binomial distribution, and the binomial distribution is going to look like this. So, that means I can write, so probability of having n1 steps, probability of having n1 steps is probability distribution essentially of having n1 steps out of a total number of steps which is the capital N, is equal to p to the power n1, q to the power n2, and then what am I going to have? I am going to have n factorial, okay, by n1 factorial n minus n1 factorial, right, because see I have just pooled them into two groups, and remember these groups are entirely independent of each other. I can select them at random. Okay. So, then this is your binomial distribution, and let this be equation 4, okay, and this is the probability distribution of having n1 steps out of a total of n steps. So, we already have it. Okay. Now, what it boils down to is, it boils down to simplification based on some other assumptions. Okay. But before we do the actual simplification, what we will do is, let us be like a coin flip process. Let us rather consider it, to, so let us consider it to be like a coin flip process. Now, why am I taking a coin flip? What happens, what are the options you have in coin flip? One is head or tail, that means p is equal to half, q is equal to half, isn't it? So, what I do is then I invoke exactly the same thing. That means, I say that here p is equal to half and q is equal to 1 minus p, which is also half. Remember, I am trying to simplify it, right, okay, and there is no problem in doing this. Okay. Now, once I do this, you put this in equation 4 and see what happens. Then p n1 n is equal to, see I have p to the power n1, q to the power n2, right. Then it would be half to the power n1, half to the power n2, right. Then my factorial form, factorial. Now, if this is how we write it, what about this term? What would it simplify to? Half to the power n, isn't it? So, see now n has come in, because my probability distribution is only based on n1 and out of n, right. I should not be having n2, that is the point. So, then I can write p n1 n is equal to half to the power n factorial n1 factorial n minus n1 factorial, and this would be equation 5 for me. Okay. So, this is my basic probability distribution, where I have taken p to the p is equal to half, q is equal to half. Remember, all the movements are statistically independent of each other. Okay. Now, I will have to do a simplification. Okay. The first simplification we would do is, we would try to simplify what? We will try to simplify this part where we have the factorials in both the numerator and the denominator. Now, before doing that, let me tell you what essentially we are trying to do. What we are trying to do is, we are going to maximize the probability in terms of n 1. Okay. We are going to maximize the probability in terms of n 1. That means, we are going to look for that number of steps n 1 where the probability becomes maximum. So, in that case what we will do is, we essentially will have to look for what? Del p over del n 1, is not it, because we are going to maximize in terms of n 1, and if we equate it to 0 and then get that number of steps n 1 where it becomes maximum. But we will not do del p, instead what we will do is what? We will take the natural log and then do it, because it will be easier for us. You will see, because we have these factorials and all those things, and we can do a further approximation. Okay. But first let write this. If I take the natural log of this one, then I can write natural log of p n 1 semicolon n is equal to n natural log half, okay, plus natural log the capital N factorial minus ln n 1 factorial minus ln n minus n 1 factorial, and this is say equation 6. Okay. So, having taken the natural log, now tell me what other approximation can I use? Stallings approximation. Yes, the assumption is that my n and n 1 are very what? Large. So, okay. So, what I do is use Stallings approximation, and what is Stallings approximation? Is equal to n ln n then minus n, right. This is Stallings approximation. Let this be equation number 7. Right. So, we take this and we put it back in our equation number 6, then we get ln p is given by, the first one stays as it is, n ln half. Now, what are the next one? We get now n ln n minus n, okay, right. Now, the next one has a negative sign. So, what should I write now? Should be the first one, should be minus n 1 natural log n 1, then what should I write? Plus n 1, right, and then I would be having minus n, tell me what, n minus n 1 natural log n minus n 1, the next one is plus n minus n 1, right. Okay. So, what will it come to now? Therefore, ln p n 1 n is equal to, see this n cancels, right. So, this one cancels with this, is not it, and this one cancels with this. Okay. So, it is already simplified for us a lot. So, I have this is equal to n ln half plus n ln n, where n being capital, minus n 1 ln n 1 minus n minus n 1 ln n minus n 1, okay, and this would be say equation number 8, right. So, just running out of space, but anyway I will write it, equation number 8. Okay. You are with me until this point, right. Now, what you do is, remember we have to maximize it. So, what we say is, now having done this, maximize the probability p n 1 n with respect to n 1. That is, I am trying to find the number of steps n 1 for which p becomes maximum. So, then what I do is, I calculate ln p over del n1, okay, at n1 is equal to n1 star. So, that means what I say is at n1 star what I get is the maximum number of steps, right, that is what I go by. So, let us do that. So, therefore, del ln p by del n1. Now, look at that equation. The first one, what would it become? The first term 0, very good. Now, the next term again 0, excellent. Okay. Now, the next two terms would be a combination of two terms, right. Okay. So, I have minus n1 ln n1. Now, tell me the first one is minus ln n1, right, and what is the next term? Minus 1, is not it? Someone really likes 0. Okay. Now, what about the next term? You have to be careful because we already have a negative sign before n1, right. Okay. So, the next one would be plus ln n minus n1, right, and what are the next one? It will be plus 1, right, it will be plus 1, right, because n is a constant anyway. So, n minus n1, it just n1 is a variable. So, hence del ln p over del n1 at n1 is equal to n1 star is given by natural log of ln n minus n1, right, then minus ln n1, and this say would be your equation number 9. See, I am telling it is n1 is equal to n1 star, I have not yet put in n1 star, but you can realize that essentially finally that is what we will put in, n1 is equal to n1 star. Okay. Now, if you are going for the maximum, what will happen to this? This would be equal to 0. Now, remember this, we are telling it is maximum, but just showing 0 does it prove that it is a maximum? It does not prove that it is a maximum. You are telling me this now, what happened to you during the exam? The question was, you show that whether it has a maximum point of stability max, except one of you, except one person, none of you showed that. चलो है क्लास में क्या था, सामने तो था कुछ, चलो लिख डाले उसको, क्या है, सोचने की क्या बात है. But you have to show this, you have to prove that there is a maximum point. How do you know that it belongs to the maximum? What would you do? You would take the double derivative, right? That is your proof. Anyway, better luck next time. Okay. So, what this becomes is 0 is equal to ln n minus n1 minus ln n1. Now, what I will do is I will put n1 star, okay, or n1 over n minus n1 star is equal to 0. From here, tell me what will n1 star be? इतना सोचने को बाप रे. When do you have ln equal to 0? What happens to the factor? It is 1, right? You equate it, you will get this. Now, tell me, does this result make sense to you or not? See, think about it logically, it has to make sense, right? I have no bias in which direction I have to move. If I have a statistically significant number of steps taken and I have no bias, then what will happen? I would take the equal number of steps in the positive and the equal number of steps in the negative, which essentially would be n by 2, and that is what you just derived. Okay. Right. So, that means at least one of the points which is extrema would correspond to n1 equal to n1 star, which is equal to n by 2, right. Very good. Now, how do you know that this corresponds to maximum? How would you know that? You take the double derivative, right? You take the double derivative. So, this is the question you are trying to answer. You have to see what question you have been asked. You cannot just go ahead and answer it. So, looking at this, what I do now is I say I try to prove del ln2 p by del n1 at n1 is equal to n1 star. That is what I have to see. If it is maximum, what will happen to this? Will it be negative or positive? It will be negative. That means I have to show that this better be negative for that to be maximum, isn't it? Okay. So, we already know, again let me write it down, ln p where was equal to what? Was equal to well, del ln p, del n p del n1 was equal to ln n minus n1, right, minus ln n1. Okay. So, now what I am doing is I am just doing the double derivative of this. So, del 2 ln p over del n1 square. So, this should be squared, I forgot to write this one, is equal to, now what about the first one, minus 1 over n1, and the next one n1. Okay. And remember, this is where are we doing it? This is we are doing at n1 star. So, what I can now write is, if I now put n1 is equal to n1 star, I can write this as n1 star. Is it okay? Right? If you put as n1 star, how can I simplify it further? What do we know n1 star is equal to? N by 2. So, then the first one is n by 2 and the next one is n by 2. Okay. So, what should I have? Minus 4 by n, and it is less than 0, isn't it? It is less than 0. So, this is less than 0, hence proved that this n1 star, whatever you calculated by equating the derivative to 0, corresponds to the maximum number of steps taken in the positive direction. Clear? Okay. Good. So, if that is the case, we already have this, right. So, what now we can do now is, so we had this p. So, what was p? Let me see, start with, it's easy to see from here. Okay. So, now what we do is we do a Taylor series expansion round n1 star, assuming that the probability peaks there. Okay. Assuming that the probability peaks at a certain point, and hence we do that. Okay. So, we do a Taylor series expansion for ln p. So, if you do a Taylor series expansion for ln p, so therefore, what we can write is, I am not writing the stuff in brackets. So, this, well, let me write then, is equal to, remember I am doing it at n1 is equal to n1 star, I am doing it around the maximum because that is where the maximum is. So, this should be ln p, remember n1 is equal to n1 star. So, I write n1 star n. Okay. That is the first term. Okay. Now, what are the subsequent terms? You have seen this before. Where have you seen this? Where have you seen this before? At least give me one relevant example from quantum mechanics. Where did you do this expansion? see the next thing would be a first derivative, the next thing would be a second derivative and so on, that is how Taylor expansion goes. But where have you seen this before? Harmonic oscillator, thank you. Harmonic oscillator, remember what did you do? You expanded the potential V, the Taylor series expansion round its minimum, right, and that is how you recovered what is the expression for k equal to, and then you went for a Morse oscillator. So, k is equal to del 2 V over del x squared, isn't it, and which is the curvature of your harmonic potential. So, that is why that example is so important. So, you do the same thing out here. So, this then this becomes plus n1 minus n1 star del ln p over del n1, n1 is equal to n1 star minus half n1 minus n1 star squared del 2 ln p over del n1 squared, n1 is equal to n1 star. Now, that is I mean that is essentially where you are doing it, sorry, that is essentially where you are doing it. Okay, you are doing the Taylor series expansion like this, all are positive quantities. How can we simplify this now? Tell me. I have to use this. So, what would this equation number be? Can someone help me? Say this is 11. I have to simplify this now. How would I simplify this? What will happen to the second term? Tell me. If I am doing it at the maximum, what will happen to the second term? It will go to 0, right? Okay. So, that means this one is equal to 0 at the maximum. Okay. So, if that is so, then I have from here natural log of p n1 n is equal to p n1 star n plus half n1 minus n1 star squared, okay, del 2 ln p over del n1 squared at n1 is equal to n star. Okay. This is my next equation, say this is equation 12. Now, tell me another simplification. What can I do now? Remember, everything is being done at n1 is equal to n1 star. Can I put in anything for the second derivative? Minus 4 by n, right? We just figure that out. So, then I can write. So, now I will replace this p n1 n by ln p is equal to ln p star. I will just say p star because that corresponds to n1 is equal to n1 star. Okay. Then this plus half n1 minus n1 star squared, and this is what, minus 4 by n. Okay. Or I can write ln p over p star is equal to n1 minus n1 star squared, this negative sign comes here, right, this 2 cancels, I have 2 by n. Okay. So, now I can write p is equal to p star e to the power minus 2 n1 minus n1 star square by n, and this would be 13, and this would be 13. Right. Now, see, we started with what? We started with the goal of trying to develop what, a probability distribution in terms of the distance that I am moving when I am making a random walk. I am still not there though, but what I have done at least is I have done, or we have been successful in getting a relationship of the probability of what, n1 out of a total number of walks which is n, okay, and this being related to p star by this exponentially decaying function. Okay. This is from where we go forward and then try to get a relation in terms of x. So, that means the next step is introduce x. The next step is introduce x, that means the displacement. And how do you do that? To introduce the displacement x, now remember from before, what was m equal to? Can you remind me? What was m equal to? 2 times n 1 minus n, right? Okay. Now, what did I say? That my x, which is the distance moved, has to be x equal to m times L. This is the distance moved in the positive direction. Now, what about L? I am taking L to be 1, right, because each step is of unit length, right. So, then essentially I replace m by x, which is x equal to m. Now, keeping in mind that you are not making any, you are not running into any dimensional problem, because you have already taken L equal to 1. So, therefore, what I write is x is equal to 2 n 1 minus n, or remember what are we trying to find? We are trying to find something in terms of x, right. That means we have to replace n 1 by what? X. So, that is what we are doing now, right. So, that means n 1 is equal to x plus n over 2, and this is number 14. Okay. So, you are done with n 1, where you have replaced this. Now, go back to your equation number 13. What do you have? What you have is n 1 minus n 1 star. You know what n 1 is? So, let us do this first. Now, n minus n 1 star is equal to 1, or rather is equal to what? X plus n by 2. Okay. What is n 1 star? Right. Then this is equal to what? X by 2. So, star is equal to x by 2, is not it? Okay. So, let this be number 14. So, now do we have x? Do we have x coming in? Yes or no? Okay. So, now you write the probability distribution. Essentially what you do is you replace this n minus n 1 star by x by 2 out there. So, what will happen is therefore, using 14 in, no, this should not be 14, this would be 15, I guess. This is 15. Using 15 in 13, we have P is equal to P star, P is equal to P star, then e to the power minus 2, this is n minus n 1 star, then whole square, right. So, what would it become? X square by 4 n, right, or P is equal to P star e to the minus x square by 2 n. This P star. Okay. Now, you have to tell me what is the significance of this result. First of all, tell me what type of a distribution is this? Okay. It starts with a G. It's a Gaussian distribution. It's a Gaussian distribution, right. So, try to appreciate the significance now. If anyone asks you for a random walk, a person exhibiting random walk or any particle exhibiting random walk, how would you describe its probability distribution? You would describe it with what? A Gaussian function. That is why a Gaussian function is so important. So, you did not know about this before. So, that is why if you look at any distribution coming from a random walk problem, the distribution would always look what? Gaussian. Why? Because this is the basic equation or the fundamental equation for a particle or a person or a species exhibiting random walk. Clear? Okay. So, we can write then this is a Gaussian distribution. See, but we are not yet done. What we now need to do is we do not have the full probability anyway, or rather yet. That means, we have p is equal to p star e to the minus x square by 2 n. X is a variable, not a problem, n is a constant, we can define the number of steps. What do we need to figure out? We need to figure out p star. How would you do that? But n that would come back. Tell me an easier way, that will not cut it. How would you, oh okay, if you would have a function like this, right, let us see this. If you would have a function like this, right, p is equal to p star times this exponent, right, e to the minus x square by 2 n. If I would have told you that p is a wave function, psi is equal to something times this, what is that something? What is that something known as? Normalization constant. So, do a normalization constant, what do? You take the whole probability over all space and equate it to 1, that is what you do here. Okay. That means, to get p star, we do the following, because we know that the total integrated probability has to be equal to 1 if it is a normalized probability distribution. So, we say minus infinity to plus infinity p of x d of x is equal to 1. Okay. Now, remember, is p star a constant or not? It is a normalization constant, right, because what? P star comes from n is equal n1 is equal to n1 star. We have already defined n, the capital N, and we have already defined what n1 star is, right, which is n by 2 in this case. So, because that is a constant, what I can write is, I can write, so here if it had been a quantum mechanical problem, what would you do? You would do psi star psi, but then psi star psi is actually your p of x, is not it, because psi star psi is your what? Bond's interpretation of probability, because psi star psi is your probability density, then you multiply it by d of x, you get the actual probability, right, it is called the probability density. But hey, you do not have to do that, because this is itself the probability for you, right, p of x, that is itself the probability. So, what you do is, that is what you said, you wrote it here because p of x is the probability, then this would be p star minus infinity to plus infinity e to the power minus x squared over 2 n would be equal to 1, okay, or p star is equal to 1 by minus infinity to plus infinity e to the minus x squared by 2 n. I should be writing d of x here, d of x. Okay. Now, there are standard integrals for this. Now, how do we do it is, so that is what you are doing. How you do it is, remember 0 to infinity e to the minus x square, say this minus a x square, sorry, let me write again, okay, 0 to infinity e to the minus a x square d of x is equal to 1 by 2 root over pi by a. There is a standard integral you are going to use. Okay. So, there is a standard integral, you are going to use. Okay. Now, I have given you 0 to infinity, but my actual integral is from where to where? So, what do we do now? We multiply it by 2, but can you always multiply it by 2? It is an even function. It is an even function, right? Only if it is an even function you can multiply it by 2. So, if you remember your harmonic oscillator problem, I always go back to that, because it has that even odd problem, even odd parity. If you remember, if you take x, then it would automatically go to 0, because you have an odd problem. Then you go to x squared, obviously it would not go to 0. Okay. So, based on this, so using this in the previous equation, so let me write this equation as 17. Okay. So, using this in 17, what you will see is p star is equal to 1 by root over 2 pi n. Okay. P star is equal to 1 by root over 2 pi n, you can check, and therefore, and therefore, now you have p of x is equal to p star, which is 1 by 2 pi of n e to the power minus x square by 2 of n. So, this is equation number 18, and this is the probability distribution of a particle exhibiting random walk in one dimension, in this case the x direction. Okay. So, I will not go further, I will stop here, because from here, see, before ending the class, what I will just write though is, if this is of p of x, if this is your p of x, suppose we try to have the average of x. Suppose we try to have the average of x. Now, what would I do? How would I get the average of x? Integration of is equal to, so remember this is already the probability density which is given to you, right. So, this is minus infinity to plus infinity, then I write x p of x d of x, simple, again enforcing the fact that you are already given the probability distribution. You do not do p times p, because this p is already the probability, it is not a wave function. Okay. Now, tell me what will it come to? 0. Can everyone recognize why it will come to 0? Why? Because x times, you leave that constant out, e to the minus x square of 2n, it is an odd function or even function, it is an odd function. So, this would go to 0, because x e to the power minus x square over 2n is odd function, it is an odd function. Now, since I am already here, just let me write the other thing down. So, you can realize one thing, why do people talk about mean square displacement or the square displacement, why not actually the mean displacement? This is the reason. If you would go for the mean displacement, what would you get? You would always get 0, is not it? See, and that makes sense. Why does it make sense? What makes sense is, if you take n steps, there is no bias, the number of steps in the steps you take in the positive direction would be equal to what? The number of steps you take in the negative direction, and hence it would be 0 anyway. Okay. Given you have enough statistical distribution, it is a large sampling size of n. So, what then we do? We always go for x square. So, even if you have negative, it becomes positive, right, and that is why people are so interested in x square, that is the sole reason. Okay. So, then if you are going to go for the mean square displacement, then I have x squared. Okay. So, this x squared is equal to, again the same way, plus infinity x squared p of x d of x. Okay. Now, what you would get from here is, I will tell you, this is also standard integral. So, what I can write is 1 by root 2 pi n, then minus infinity plus infinity x square e to the minus x square by 2 n d of x. Now, there is also standard integral which is given to you for this. The standard integral is 0 to infinity x square minus a x square d of x is equal to 1 by 4a. I mean, let me look at, I do not want to give you the wrong one, root over pi by a. Okay. This is your standard integral, this is what you use. So, remember this would be 2 times of this, okay, and hence what you would find is x square is equal to n. What you find is x square is equal to n. Okay, this is just left as a small exercise for you to complete. Okay. Okay, guys, this is where we end with the statement. What it says is, if x square is equal to n, that means your mean square displacement is equal to what? The total number of steps, right. Now, if you take the root mean square displacement, what will it go, or where will it go? If you take the root mean square displacement, it will go n to the power half. Now, this is the basic difference between something exhibiting a random walk and something exhibiting a directed walk. If it is a directed walk, what would you expect? You would expect it to be linearly proportional to n, but in this case what you are getting is finally your x square half, which is the root mean square, is equal to n to the power half. Okay. So, this is the RMS, the root mean square displacement, that is equal to the square root of the number of steps you are taking. Again, this is a typical characteristic of a random walk problem. Okay.